Okay, so yes, if you were wondering why a product manager is going to give this talk in a technical track, it is because I did change roles. So yeah, just to get rid of a little bit of that strangeness. So this is the disclaimer side, which needs to be on there. I've agreed to it, but let's not dwell on that. PQC signatures are too damn big. Did anybody here read the blog post by David Adrian that came out a few weeks ago? Show of hands? Okay, there's one there. Anybody else? If you haven't, please go and read it. It's very, very well written. So we have 3 signatures that NIST are standardizing, and we're expecting these pretty soon. The first 2 are based on lattices, and the third is Sphinx, right? It's colossal, it's based on hashes. Now, in this blog post, he goes through and he says, right, the average TLS handshake for HTTPS contains around 5 signatures and maybe 2 public keys, considering, certificate chains and everything. With the current quantum vulnerable stuff, this comes out at about, 1.3 kilobytes. And with ML sign, which is what NIST has imaginatively renamed dilithium, this is an order of magnitude larger, right? So this is really going to be a pain. And what this work revolves around is, it's the idea that can we make this PQC slightly easier to adapt for certain use cases? So we defined this concept called batch signatures. Actually, I don't know whether we defined the actual concept, but we characterized this specific version by a triple of algorithms, keygen, which is essentially corresponds to like a normal digital signature algorithm, batch sign, which is where we take in many messages, and we produce many signatures. So this is many to many, and verify, which is where you take in just a single message, a single signature, and you say, accept or not. So remember, batch sign, many to many, verify is one to one. And we would like some properties from this. Batch privacy says that no efficient adversary can learn whether signatures were signed in the same batch. Weak batch privacy says that if you've got a signature for, I, it doesn't leak any information about a different signature, signature J, in the batch if signature J isn't available. And in our construction, we managed to prove weak batch privacy, but not batch privacy for a good reason. So do we have any Merkle tree fans in the room? Again, I want a show of hands. Okay, this is good. Now keep your hands up if you consider yourself a Merkle tree expert. Okay, we've got one. I'll be careful. So essentially the gist is that you collect a load of elements at the bottom. These are your muse. These are like messages, maybe your TLS transfer. And what we're going to do is we're going to iteratively hash them, okay? So you traditionally take say like a left and a right and you hash it and you get a parent node, and then you take a parent node and the parent node to the left of it and you hash it. And eventually you end up with a root of the Merkle tree. The hashes at the bottom are the leaves, and the top is the root. And you end up with, if you've got 8 at the bottom, you'll end up with log of 8 depth. And each one of these points is going to have an address. The address is very important, which is basically how far along it is and how many, how deep it is. Now, what we have is these tweakable hash functions. Now, tweakable hash functions are like a form of keyed hash function, only they have this additional domain separator. And again, you can define it as a tuple of algorithms, which is basically, you generate some kind of key or public parameter, and then, you hash it and you get a digest. You can create these with normal, like SHA-2 type hash functions. You just add in extra parameters. And these parameters that it takes are P, which is a public parameter. Think of that as your identity. It takes in T, which is a tweak. This is the address of the node in the tree, right? Remember I said that each one has like a specific address. And the mu is the message. Now, the reason that this is going to become quite important is because when an attacker wants to break your your hash functions or your Merkle trees, we really want to force them to specifically try and break a particular location. So if I've got one public parameter and you have a different one, then we're going to have different P's, right? And we don't want an attacker to be able to just say, right, I'll find a hash collision on either of those. And even within that tree, we want them to target a specific location. And this reduces all the combinatorial ways in which they can subvert the system. So the fundamental properties that we want this to rely on, traditionally we've used collision resistance, and versions with Merkle tree type signatures have often used collision resistance, which is essentially you get one message, hash it, can you find two different messages which are different but which hash to the same thing? This is very hard in general, but for example, MD5 is completely broken there. But you need a certain hash digest length. If you use this new hash function property called single function multi-target collision resistance, so named to deter anybody from kind of reading further into the details, then what you find is it's kind of a different setup, but it relies much more closely on second pre-image resistance. And what this means is that ultimately it enables you to halve the hash digest length. So in this, the model is something like you fix the tweaks, so the location on that hash, on that Merkle tree that you want to attack, and a message. A public parameter is then revealed to you, right? So this is interactive. That's why it's weaker, because of this interaction. And then you have to find a different message such that with the parameter which has been fixed and the tweak that's been fixed, you get a collision there. So it's single function, multi-target collision resistance. I believe that this property was introduced to basically help the Sphinx plus proofs. And this is something which Andreas helped us out with, Andreas Hulsing. He's like the hash function signature beast, if anybody are familiar with Andreas's work. So now we can cut to the actual construction. We're going to start off by drawing our identifier, some random number in the security parameter. We're going to collect n of these messages. And then we're going to draw some leaf randomness, and we need this to kind of prevent collisions at the leaf level. And at this point, we have enough to evaluate the leaves of the tree. So the leaves are going to be this thing, all down there in that pink hoop. Once you have all of the leaves, you can then go through and you compute the next layer, then the next layer, then the next layer, and eventually you are going to get to the root, which is T30. You then sign the root using a traditional signature, right? So this is where your PQC goes. You have a root of the tree, you sign it, and you get some kind of normal traditional DSA signature. And for each of the messages that you're signing, that signature is essentially the signature at the top from the conventional signature, this sibling path, which are the blue circles, and everything you need to construct your leaf. Now, if we take a look at construction 2, which is this verify thing, then what we have here is we reconstruct the same thing. So we generate all of these, so we build the leaf. We then hash it with every member on the sibling path, so that eventually you can reconstruct the root. And then you take the verification key and the root and the traditional signature algorithm, and you check if it works. So you verify this the root signature with PQC. and that gives you an accept or decline result. Now, if we look at the security proofs, how does this actually work? Well, the setup is that you have some kind of polynomial time adversary, which is, it's somebody sat around with a very powerful computer who can just, he's got access to the public key, because it's public, and he has access to a signing oracle, so he can submit messages and get signatures back, and that's all he's got. And because he's polynomial time, he can generate Q of these queries, where Q is going to be a polynomial in the security parameter. He's going to store all of the results, which are a message and a signature pair. And he's going to store all of these in this set that we call big Q. So at the end of this, he's just got this huge database of signature message pairs. At the end, he is challenged to output a message signature pair for a message that is not in Q. So the signature can already be in Q. You can have seen the signature before, but the point is he has to forge, given that he doesn't have the private keys, he has to be able to produce a forgery that tells him, for a message that has not yet been seen. So there are two ways this can happen. Either the root of that Merkle tree was not already in Q, so he hasn't seen it before. In this case, you've essentially found a subroutine that can allow you to break the EUF-CMA property of the underlying signature scheme. And this is something that we don't touch. This is something that we presume already exists. Otherwise, people should be moving forwards and standardizing these things. Or the root already is in that database, in which case there is a collision somewhere in the Merkle tree because the message at the bottom, which gives you the leaf, is different, but somehow the root matches a root of a different tree. And what this means is that you can just trace down to where the nodes at some point differ in these two trees, and you can extract a target collision which breaks this property SMTCR. And if you can break SMTCR, which we think is, we have pretty high confidence in a lot of the security properties of these hash functions, then, big trouble. So these are the two ways that you can, that a forgery would imply either you break a hash function property or the security of the actual DSA that gets plugged in at the top. So why does any of this matter? We'll check out what the performance implications are. First of all, we have speed. You can expect a small amount of additional latency here. Now, the reason why is because before we were signing something maybe with dilithium, and now we're signing something with dilithium, but we also have to, buffer a load of messages, wait for everything to come through, and then create a Merkle tree. This is going to create a very small amount of additional latency by comparison, but the trade-off is that you can then amortize this over like a huge batch. So if you look over here, you can see in P99 that generally the latencies are a little bit higher for the batch versions, about 50% more for the lower rows than the top rows in this instance. But the thing is, the lower rows are like, you get 16 signatures here versus 1, 32 signatures here versus 1. So the throughput can be massively boosted, even though, the throughput can be massively boosted, even though the speed might take a small hit. Now, in size, there are also some nice benefits, which is that we can get huge compression. It turns out that there are many use cases where it's reasonable to expect that you might receive many signatures from the same signer. Where this is the case, we do not really need to worry quite so much about needing to send the same signature over and over again. So if this right-hand hoop is actually around the wrong thing, it should be over these. But so take this signature, this is the DSA signature. For ECDSA, it's kind of not too bad, but for dilithium, it gets pretty big. For Falcon, it's pretty big, and I'm not even sure we bothered with Sphinx. Now, this thing, which says send many times, should actually be here. And this is the sibling path that I talked about. So if you already know that you're going to get this dilithium-2 signature, and it should be the same because it's from the same signer for the same batch, then in the future you only need to send the sibling path. You have to really work out whether this matches your use case, but if it does, then this could be, this could be a pretty killer way to boost the adoption of PQC, because you can see with ECDSA, 64 bytes, but for anything PQC, this is going to make a huge difference. So now that I've talked about the potential throughput advantages and the size advantages, let's check out a couple of applications. So this is where you have, say, an HSM, and it's generating certs for a bunch of Envoy instances who communicate via MTLS. So if you consider that all of these instances are part of one batch, then they're all going to have the same root signature, which means that when they communicate with one another, they don't need to send their own root signature because they already have that in their own certificate. And finally, consider a load balancer or a TLS proxy. So at the moment, what we have is internet traffic going through the roof. We have, more devices, more connections. We have the actual amount of, the proportion of data being encrypted also going up, and now we have to transition to post-quantum cryptography. So all of this is a bit of a brewing storm for, for load balancers, or, if you have signing threads that are trying to keep up and generate enough signatures. And this causes a huge strain on even actually the bare metal devices. They wear out quicker. So during a high demand period, you can switch to reduce the computation by batching your transcripts. In this instance, okay, you might be sending the same root signature to different people, but the point is the bottleneck here is on the computation and the throughput. So the previous example shows you the benefit of the compression, and this benefit shows you the example of the benefit of higher throughput. So there are different use cases where these things can be really valuable. And yeah, that's pretty much it. So thank you for listening, and I'm happy to take a few questions.
So what would it take to put this into practice for one of the scenarios that you put up, just to kind of give us an idea? So take maybe the scenario with the HSMs backing up a mesh network with Envoy proxy. What would it take? What's the delta between where we are today, if we were just to kind of naively implement those signatures, to actually putting this into practice?
Yeah, that is a very good question. I think what we need to do is organizations who run this infrastructure, so it really has to start with the organizations who run this infrastructure. They have to, first of all, identify a use case, work out whether it is really a bandwidth issue or whether they're going to run into a throughput issue. And generally, what would usually happen is they'll start off by benchmarking, figuring out whether PQC is going to work in their next applications, and they're going to find out, okay, this is going to be pretty rough. At that point, I guess you start looking for solutions, and maybe this comes up as one of them. Probably the most difficult part of this is identifying, what are the use cases where this is really going to make a big difference, right? Because that's not trivial. I remember when I was discussing with one person from a large internet infrastructure provider, they said that the throughput and the actual latency of getting overloaded by PQC signatures might be one thing, but they're not so worried about that. But the difference between actually saving the amount of bare metal sort of wear that they get from actually just running through, repeating like a full PQC signature over and over and over again, that could be quite appealing. So Yeah, this is difficult to figure out, but in terms of actually implementing the Merkle tree and then moving forwards with that, it's pretty doable. So the infrastructure piece, difficult. The implementation piece, it's not rocket science.
Okay, just one supplementary question. Would it need to go through a standardization, or is this something that an organization could just choose to adopt on their own?
There are standards processes working on things which are kind of like tangential or similar. So Merkle trees have definitely found their ways into a number of different IETF standards in various different forms. In terms of would you be able to implement this proprietarily, I think that you probably would, but it would need to be some kind of application or use case where you really do have control over all of the endpoints, because you do actually have to change the actual signing mechanism and source code and stuff. So yeah, you would have to have a lot of control or go through the standards bodies.
Thank you.
Really quick question. You talked about the verification portion of it. How is the performance of the verification?
So the verification is essentially computationally almost the same, which is you have to compute maybe 5 or 6 different hash functions, which are like almost free, and then you have the verification of the actual digital signature. So that is going to be dominated, I would expect, by the verification of the traditional signature. So again, probably very similar to what you'd have to do anyway, but with a small amount of extra work.
Okay. Is there an article that you're basing this on, like a scholarly paper?
Yes, we have a paper that I can share with you, Batch Signatures Revisited. There is an IETF draft, I think, as well. No, there's definitely an IETF draft. And maybe we have a blog post we can share with you as well.
Thank you.
Hi. So Merkle trees are a type of vector commitments. Have you tried other vector commitments, maybe constant size ones, like KZG commitments? Why did you choose Merkle trees?
So, good question. Why do we choose Merkle trees? I think probably because we started with some Merkle tree experts, and we thought, what can we do with this? This is pretty interesting. Have we tried other sort of compression or speeding up methods? At this point in time, no, not yet.
So it's not speeding methods. So vector commitments. So Merkle trees have logarithmic size proofs. So when you're batching, you're going to have to be bound by that logarithmic.
Yes.
Right. So the more things you batch, the bigger the size of your signature. It's no longer constant size. So
yes. So this would probably make most sense if we were to constrain batches to say like size 32 and just say like, yeah.
There are other types of vector commitments, for example, KZG commitments, that have constant size signatures. You can just use that. Of course, I don't know why you didn't, but that's what I was wondering.
Interesting. Let's talk about this afterwards. Thank you.
Welcome everybody. I'm Edoardo Signorini. In this talk, I will present a general framework to build sequential aggregate signature from hash and sign schemes, including and particularly for post-quantum ones. So, this is the disclaimer. Okay. Let me start with the brief background. So, with an aggregate signature, we can combine n distinct individual signatures from distinct signers on possibly distinct messages. And the goal is to have a single aggregate signature that can be directly verified, and it is shorter than the trivial concatenation of the individual signatures. So this is useful whenever you have to send a large number of signatures and you are in a network constrained environment, so sending many signatures would be quite costly. Now, there are different approaches to aggregation, and in the most general case, aggregation is a public function that can be computed by a third party without requiring the interaction of the signers. And historically, this has been done mainly with bilinear pairings. But we can also consider somewhat a weaker model where the aggregation is done iteratively in a sequence by each signer. And these are known as sequential aggregate signatures and can be built from any trapdoor permutation, such as RSA. And we will focus on the latter, but a relevant question in general is whether we can build aggregate signature from post-quantum assumption. And okay, perhaps unsurprisingly, the quick answer is yes from lattices. And in the general case, there are some very recent approach with the non-interactive argument of knowledge, with SNARK, while in the sequential case, there are mainly two directions from lattice assumption and multivariate-based assumption that both develop on existing frameworks from trapdoor permutation. But when we first approached this problem, we noticed that the multivariate-based construction were actually insecure because multivariate trapdoor function lack some stronger properties from permutation or from lattice function. So our goal was to effectively extend the existing framework from trapdoor permutation to generic trapdoor function and then apply it to multivariate-based function and to other ancient sign schemes. So my plan for the talk is to give a simplified description of the aggregation step, and I want to start with the case of permutation, which is simpler. And so here, the underlying signature scheme that we want to aggregate is the well-known full domain hash paradigm, and this is probably the other big paradigm together with Fiat-Shamir signatures. So here, our public key is a permutation, pi, and our private key is some secret information, the trapdoor, that allow us to invert the permutation. And if we want to sign a message M, we take the hash of the message into the domain of the permutation, and then we use our secret information to find a preimage that will be our signature. And verification is straightforward since we just apply the public permutation on the signature and we compare it with the hash of the message. Now, if we want to aggregate this kind of signature, the basic idea is that we take the previous signature, the signature from the previous user, and we embed it into the domain of the permutation. So if we want to add our signature on top of the previous one, we take the hash of all messages and public keys from previous user, we combine it, we XOR it with the previous aggregate signature, and then we find a preimage that will be our new aggregate signature. And verification here is still straightforward. Again, we just need to invert the process. We start from the last aggregate signature, we apply the public permutation of the last user, and combine with the output of the hash function to retrieve the previous signature. And then we can iterate this process until we get to the first signature that can be directly verified. Now, notice that in terms of efficiency, this is not different from trivial concatenation, since you still need to do n signatures and n step of verification. But from an aggregation point of view, this is optimal because the size of the aggregate signature is equal to the size of an individual signature. So you have constant time aggregation, constant size, aggregation, and it is independent from the number of the signers. Now, the problem when you try to extend this approach to post-quantum assumption is that the full domain hash paradigm does not translate too well in the post-quantum setting because now you don't have trapdoor anymore, you have some generic kind of trapdoor function, and so you need to tweak this construction. So for the rest of the talk, we will consider generic trapdoor function, meaning that instead of having a public permutation as our public key, we will have some generic efficient function f that in general will not be injective, And our private key will still be some kind of trapdoor, some secret information that allow us to invert the function f. But now we are also assuming that the inversion process is probabilistic and it may also fail on some input. Since we are dealing with a signature, we also assume some notion of one-wayness for the trapdoor function, meaning that without the knowledge of the trapdoor, it's computationally unfeasible to find a preimage. And now we know that if we build a signature with the full domain hash approach, and the function is a permutation, the security of the signature, its unforgeability, directly reduced to the one-wayness of the function. But this does not hold in general, because when we move to generic trapdoor function, we lose some uniformity properties. In particular, we have no guarantee that a preimage sample during the signature will be uniformly distributed in the domain of the function. And this is crucial for the simulability of the signature. So to recover probable security, we need to move to a slightly more general paradigm known as probabilistic hash and sign with retry. And so here, if you want to sign a message M, you just sample a short random element that we call a salt. And again, you use your secret information to find a preimage. But now the signature will be given by both the preimage and the random salt. And if this process, if the inversion process fail, you just sample a new random salt and retry the process. And now the security of this signature scheme reduces to both the one-wayness of the function and to an additional notion that was recently introduced that basically ensure that thanks to the role of the salt, the preimage is undistinguishable from a random element in the domain. So again, this is something that we have for free when we work with permutation, but not in general, and this notion allows us to recover it. So we are finally ready to describe the extension of the aggregation process to generic trapdoor function. And here the very first basic observation that we can make if we start with the aggregation step that we described earlier is, since we are not dealing with the permutation anymore, in general we cannot hope to embed a signature, which is an element of the domain of f, into the range of the function. And so the idea here is to introduce an efficient encoding function that splits the signature, the preimage, into two components. The first component, which we call the alpha encoding, will be made part of the aggregation step, while the second component, the beta encoding, will be made part of the aggregate signature. And so yeah, if we want to verify, we just start from the last user preimage, and then we will recover the alpha encoding of the previous preimage, that together with the beta encoding, we can decode the previous preimage. And then we proceed as before. Now, this construction was employed with a multivariate based trapdoor function and was claimed to be secure with basically any trapdoor function, because the multivariate function that were considered do not have any particular property besides the one that we described in general. But in our work, we showed that this is not true because this aggregation process is not probably secure with generic trapdoor function, and moreover, this aggregate signature is universally forgeable when we choose some particular trapdoor function. In particular, we show an attack with the oil and vinegar trapdoor. So in the remaining time, I'd like to give you some insight on how to recover probable security, starting from the last aggregation step, and basically how to obtain our protocol. So, okay, here we are starting from the aggregation step that we described in the previous slide, and the main problem when we move to a generic trapdoor function is that the aggregate signature that we obtain is not uniquely determined by a fixed choice of the input, and which are given by the list of public keys and messages of all users. And this is a formal security problem because you lose simulability, but it's also a practical security problem because of the overall malleability of the aggregate signature. And in particular, we showed that if an attacker controls the penultimate user, they may be able to forge a signature for the last user. For example, we may change the message of the last user in the last aggregation step, and this would result in a constraint on the alpha encoding and a partial constraint in the previous preimage in sigma n minus 1. But now, if the adversary controls the previous user, they may be able to find a valid partially fixed preimage. And I won't go into more details, but this is exactly what we exploit in our attack, and we show that for oil and vinegar, it is possible to find this kind of partially fixed preimage. Now, both of these problems can be solved by making the previous preimage non-malleable, and this can be done by making it part of the input of the hash function. And now we recover security, but we lose correctness, since now it is not possible to perform the verification step. In particular, it is not possible to invert this process because to recover sigma n minus 1, we need to compute this as function, but then we need to know sigma n minus 1, so we are stuck. And to solve this, we can use a two-step hash procedure by introducing an additional hash state, short hash state H, that we will make part of the aggregate signature. And so here, the input from the previous aggregation step is now given from the previous preimage, sigma n minus 1, and the previous hash state, hn minus 1. And now if we want that to aggregate, we take the output of the first hash function, which now includes sigma n minus 1, and we use it to update the previous hash state, and this will be passed on to subsequent round of aggregation. And we also immediately expand it with the second hash function into the range of the function. And now we proceed as before because we just combine it with the alpha encoding and find a preimage. And we now have recovered correctness, since now when we verify, we start immediately from the last hash state that we can expand it, and we can combine it with the image of the last of sigma n to recover the alpha encoding, decode sigma n minus 1, and then compute finally this first hash and recover the previous hash state. So this protocol is correct, and it also not vulnerable to the attack that we described before. But similar to the plain signature, we still have some formal security problem related to the possibility of a failure for the inversion step that may leak some information on the private key. And so also for the aggregate signature, we need to adopt the probabilistic hash ensign with retry approach. And this can be done by simply taking a random salt in the input of the first hash, and as before, if this inversion step fails, we just sample a new random salt and retry the process. So we finally got to our protocol, and what is now the final aggregate signature now is given by the list of all random salt of all users used during aggregation, the last hash state, the last user preimage, and the list of beta encodings from previous users. And what we obtain is a sequential aggregate signature that is probably secure in the random oracle model, and that similarly to the plain signature reduces to both the one-wayness of the trapdoor function and to the additional notion of preimage and distinguishability that we introduced before. And okay, here in the slide I wrote that the reduction is not fully black box because this additional notion must be discussed for each trapdoor function that we consider in the aggregation. But so yes, this is clearly an additional requirement on on the scheme, but it is also a requirement for the underlying signature scheme. And so since we are dealing with sequential aggregation that are usually built on top of existing signature, this is something that we can almost take for granted. We also obtain, and we can almost say that this is incidental, an history-free sequential aggregation, meaning that during the aggregation step, we don't need to know all previous users' public keys and messages, which in non-history-free scheme are required to perform a verification step before each subsequent aggregation. So this is really an interesting efficiency property that it's almost entirely due to the presence of the random salt. And in fact, this same approach was used also for trapdoor permutation to achieve the history-free property. But as we discussed, the role of the random salt here is to recover basic security, so it's not something that we can choose to remove. And finally, on the negative side, we introduce a small overhead, a small size overhead compared to the basic scheme that we see in the beginning, given by the list of the random salt and the hash state. But yes, this is a small overhead because the size of the aggregate signature is still dominated by the list of the bit encodings, which are ultimately determined by the choice of the trapdoor function. In particular, the larger is the domain of the trapdoor function compared to its range, then the less information we can embed into the aggregation step. But still, we obtain non-negligible aggregation rate. And for example, here I reported the aggregation rates of two multivariate-based schemes, which were proposed to the NIST call for additional post-quantum signature, which are on the left classic oil and vinegar, and on the right, Mayo. And for example, for oil and vinegar, we obtain an aggregation rate of about 20%, even for a small number of signers, that grows to about 30%. While for Mayo, we have a smaller aggregation rate due to the particular structure of the trapdoor function. And but yes, these are more or less the aggregation rate that we can expect for trapdoor function based on oil and vinegar, on the oil and vinegar trapdoor, which are the good part of the multivariate-based one submitted to NIST. So, okay, I'm running out of time, so I'm going to conclude. And so in a nutshell, we started by observing that many post-quantum hash-and-sign schemes require the probabilistic hash-and-sign with the retry approach, and that many of the formal security problems that we had with plain signature also extend to sequential aggregation. So in our protocol, we adopt the probabilistic hash-and-sign with the retry approach, and we recover probable security with only a small size overhead. And as a very final note, I want to say that even if we have non-negligible aggregation, we are still far from the ideal case of the permutation that we see on the beginning, because here the size of the aggregate signature grows linearly with the number of signers. But this is somewhat inevitable with the process, the aggregation process that we described. And so a framework to build with constant rate aggregation for generic hash-and-sign signature is still an open problem. Thank you very much for your attention.
Hi, and thanks for the talk. And I saw that clearly this work was focused on the case of hash-and-sign. And do we have similar results in general for Fiat-Shamir signatures, which we have, like, we render identification protocol to a signature? Or?
Okay, thank you for the question. I would say not general framework such as this one. We try to work on some general framework to aggregate Fiat-Shamir signature, but we were only able to aggregate the challenge part of the signature, so the aggregation was very small. There are also some specific work for example, for the lithium, so for Fiat-Shamir with Abors, but also there the aggregation it's pretty small. Probably the most interesting direction now for lattices in particular are the one based on SNARK, on non-interactive argument of knowledge with succinct proof, because there you can have general aggregation with a small overhead in the size of the aggregation. But yes, then you would need a SNARK for that.
Hello. Yes. So I have a very beginner question. Like with the presentations that we've seen before on batch signatures, are there any solutions to do batch and aggregate at the same time, or like try to have properties of both? Or like and if you had to choose to use one of them, like batch signatures or aggregate signatures for different types of scenario, what would you advise?
Okay,
Thank
you. I'm not an expert in batch signature, but I would probably say that aggregate signature are a generalization because allow you to aggregate even signature from different user. So, for example, you can recover batch signature by aggregating different signature from the same user on distinct messages. But clearly, and as always with this kind of protocols, batch signature are probably more efficient in what they do compared to aggregate signature. So if you need to aggregate signature from one user, you should probably use a batch signature because even in the talk before, you saw that the aggregation rates were much better than what you can achieve here. But if you need multiple users, then you have no choice to use generic aggregate signatures. Thank you very much.